You're tuned in to Beyond the Known. It began the way many warnings do, quiet, almost overlooked. Just a streak of light, faint and cold, slipping past Neptune's orbit. No fireworks, no tail, no sound, just a presence. But the calculations told a different story. This wasn't from here. Another interstellar visitor. And this time, we were ready. In our episode on ʻOumuamua, we wondered aloud, could that strange tumbling object have been a probe? A scout, even. At the time, it was just a theory, a tantalizing one. But what if we weren't wrong? Now a second object has arrived, larger, faster, stranger. And some are already calling it the vessel. What makes it so different? What makes it so perfect? This episode, we'll explore what astronomers have observed so far. Then we'll look at the anomalies that no one can quite explain. From there, we revisit ʻOumuamua and the growing theory that this isn't just another rock, but a sequence, a message, a mission. Finally, we return to what the science tells us and what it can't. First, let's start with what we know. So this object we're talking about today, it's officially designated 3I8 Ls. Sometimes you'll see the provisional name C2025N12. It made its appearance, its detection, I should say, back in July of 2025.
That's right. And it wasn't some sudden flash across the sky. It was a very methodical detection. It came from the ATLA survey telescopes, the ones located down in Chile.
Right, ATLAS. And their whole job is basically scanning for things like this, these transient events.
Exactly. They're designed specifically for that. They perform these continuous wide field scans night after night, looking for anything that, pops up briefly or moves against the background stars, anything out of the ordinary.
Like an automated sentinel constantly sweeping.
Precisely. And that systematic approach, that's what snagged 3I8 Ls. When they first spotted it, it was just a really faint point of light. Got the label A11PL3Z initially. Not very catchy. And at that point, it was way out there, roughly Jupiter's distance from the sun. But the thing that immediately made astronomers sit up and take notice was its movement. It was moving unusually fast.
Faster than anything that belongs in our solar system.
Faster than anything known to originate here, yes. That speed was the first big clue. It was a kinematic signature, basically, suggesting it wasn't gravitationally bound to our sun. It was just passing through, an interstellar interloper.
And the location of the discovery was also pretty interesting, wasn't it? Coming from the galactic plane?
Yes, that's quite noteworthy. Many of the other big sky surveys, like Pan-STARRS or the Catalina Sky Survey, they often actively avoid looking directly into the densest parts of the galactic plane.
Why is that? Just too much clutter?
Essentially, yes. It's incredibly packed with stars, gas clouds, dust. It's visually very noisy. Trying to spot a single, faint, fast-moving object against that backdrop is, extremely challenging, like trying to find a specific needle in a massive cosmic haystack.
So pulling this one out of that region really says something about the ATLAS system's capabilities.
It does, and it highlights the perhaps unique circumstances of this detection. But the definitive characteristic, the thing that screamed interstellar, was its orbit. It's on an extremely hyperbolic trajectory.
Okay, hyperbolic orbit. Break that down for us. Not like a planet's ellipse.
Not at all. Think about throwing a ball. If you toss it up gently, gravity pulls it back down in an arc, right? That's like an elliptical orbit bound to the Earth or a planet bound to the sun. But if you could throw that ball with enough force to escape Earth's gravity entirely so it just keeps going and never comes back, that's a hyperbolic path.
They got escape velocity.
Exactly. 3I8 Ls has escape velocity relative to whatever star system it came from, and it has far too much speed now to be captured by our sun's gravity. It's on a one-way journey through our neighborhood. Tracing that path backwards, the calculations show it came from the direction of Sagittarius.
Sagittarius, so near the center of the Milky Way.
Relatively close to that direction on the sky, yes. Emerging from interstellar space from that region.
And its actual velocity, broken down, tells an even deeper story. You mentioned moving away from the galactic center and upwards.
That's right. Looking at its motion in galactic coordinates, it's moving away from the galactic center at about 51 kilometers per second relative to our sun. That's the NETIX of 51.0 meters value. And perhaps more intriguingly, it's also moving upward, sort of punching through the main plane of the galaxy at about 18.5 kilometers per second relative to the sun. That's the plus 18.5 kilometers value.
That upward motion, what does that imply?
That high vertical velocity is really telling. It strongly suggests this object isn't just orbiting within the flat main disk of the Milky Way, where most stars, including our sun, reside. Instead, its path is significantly tilted. It's more like it belongs to what astronomers call the galaxy's thick disk.
The thick disk.
Okay, so not the main spiral arms part.
Think of the Milky Way like maybe an old vinyl record. There's the main flat part with the grooves. That's the thin disk. But there's also a slightly puffier, older, more spread out component above and below that, the thick disk. It's generally populated by older stars, stars that formed earlier in the galaxy's history. And critically, these stars tend to have lower levels of heavy elements.
Heavy elements meaning things other than hydrogen and helium. Stuff needed for planets like Earth.
Exactly. Astronomers call it lower metallicity. This suggests 3 alienspaceships formed in a very different environment than our own solar system, an environment potentially much older, maybe dating back 7 billion years.
7 billion years, wow. Our sun is only about, 4.5 billion?
Correct. So this object could be significantly older than our entire solar system. It's like a time capsule, carrying potentially pristine material from a much earlier epoch of galactic history, maybe from a chemically different kind of stellar nursery. It's an incredible piece of galactic archaeology just wandering through.
And physically, it's quite substantial.
Oh, yes. Current estimates put its size at roughly 11 kilometers across. That's about 7 miles wide.
Which makes it the biggest interstellar object we've seen so far, right? ʻOumuamua was tiny compared to this.
Absolutely dwarfs it. And it's not just large, it's fast. Really fast. It's clocking in at about 60 kilometers per second relative to the sun. That's roughly 150,000 miles per hour.
Just staggering speed. Faster than the previous visitors, too.
Notably faster, yes. Its speed adds another layer to its profile. Now, its closest point to the sun, that's called perihelion, that's expected around October 29th, 2025.
And closest approach to Earth, are we talking a near miss?
Not particularly close in everyday terms. It'll pass us at about 1.8 astronomical units. And AU is the Earth-Sun distance, so 1.8 AU is about 270 million kilometers away. That'll happen in December 2025.
Still, close enough for a good look, astronomically speaking.
Definitely. It's a significant opportunity for detailed observation with our best instruments. And importantly, as it gets closer to the sun and warms up, it's already started behaving like a comet. We're seeing it develop a coma, that fuzzy envelope of gas and dust, and even a tail is starting to form.
So it is outgassing, volatiles boiling off.
Yes, classic signs of cometary activity. The increasing solar heat is causing its ices to sublimate, turning directly from solid to gas. This means that for observers, probably in late 2025, it should become visible even with reasonably sized sort of mid-range amateur telescopes.
A chance for many people to potentially see an interstellar visitor. That's quite something.
It's a rare opportunity to gather a wealth of data on an object that's traveled an almost unimaginable distance, carrying clues from another star system entirely. But even early observations hinted that this object doesn't behave quite like the others.
Right. Even as it started showing those cometary signs, there were peculiarities. Yeah. Things that didn't quite fit the standard picture.
Exactly. For instance, early observations of its coma, that expanding cloud around the nucleus, revealed a really striking symmetry. It looked almost perfectly spherical, very uniform, which is, well, unusual for a natural comet.
Why unusual? Don't they often look like fuzzy balls?
They do, but often the fuzziness isn't perfectly even. Natural comets usually have uneven distributions of ice and rock on their surface. As they heat up, certain spots become active, shooting out jets of gas and dust. This tends to create irregular, lopsided, or even fan-shaped comas.
The 3-eye lays is smooth.
Remarkably smooth, especially in the early stages. This suggested a potentially highly uniform internal structure, or a very consistent outgassing process over its entire surface. Neither of which is typical.
And there was something about when the coma started forming, too.
Yes, that was another point. The coma began to develop much farther away from the sun than we usually see for typical comets. This early onset of activity, this sublimation, implies the presence of what we call highly volatile ices.
Meaning ices that turn to gas really easily at lower temperatures.
Precisely. Things perhaps like frozen carbon monoxide or nitrogen, which vaporize much farther out than water ice does. This early activity could mean 3-Ialis holds a more pristine, less processed sample of the materials from its home system, materials that haven't been baked off yet.
Like a chemically preserved message from its birthplace.
Potentially, yes. And beyond the coma, the tail also showed some, let's say, oddities in the preliminary images.
How so? Isn't the tail just a tail?
Well, comets typically show 2 main tails. A dust tail, which is broader, often curved, following the comet's orbital path, made of larger particles pushed by sunlight pressure. And an ion tail, which is usually straighter, narrower, made of charged gas pushed directly away from the sun by the solar wind.
Okay.
Preliminary views of 3I Atlas's tail showed some subtle directional irregularities. It wasn't quite aligning with the expected geometry based purely on solar wind and radiation pressure. These deviations actually caused some initial problems in accurately gauging its size and brightness.
Because the activity wasn't building up in the expected way.
Kind of. The slow, slightly peculiar way its activity ramped up made it seem less significant at first glance than it turned out to be. It hinted that maybe more complex physical processes were involved, or perhaps something about its composition or structure was influencing the tail's behavior.
And this ties back into its origins, too. The thick disk idea.
Well, the origin itself is fascinating. Coming from the thick disk, implying that 7 billion year age. That inherently makes it different from anything formed in our younger solar system. But there's another piece of the puzzle we're still missing. Its rotation.
We don't know how it's spinning.
Not conclusively, no. Astronomers are working hard to measure its rotation period and axis. Is it tumbling? Is it rotating smoothly? How fast? Knowing the rotation is key to understanding its true shape. Is it roughly spherical, as the Comet suggests? Or is it elongated like ʻOumuamua? And maybe even its internal density or structure.
So that uncertainty just adds another layer of mystery.
It really does. And all these early, slightly unusual characteristics of the symmetric coma, the early activity, the tail quirks, the unknown rotation, the ancient origin, they started to fuel speculation. Before all the data could be gathered and analyzed, before the standard explanations could be fully tested, these ambiguities naturally opened the door for more imaginative interpretations.
The idea that maybe this wasn't just a standard comet, even an interstellar one.
Exactly. That maybe it was somehow more active or possessed a unique internal structure, something fundamentally different.
And once things stop lining up with what we expect, the imagination steps in. Not all questions lead to theories, but some demand them.
Absolutely. And to really grasp where some of the more, shall we say, fringe theories about 3I Atlas are coming from, you have to go back to Oumuamua, remember, detected in 2017, our very first confirmed interstellar visitor. Its biggest mystery, the one that still sparks debate, was that non-gravitational acceleration.
Right. It sped up as it left the solar system, but without any visible reason. No comet tail, no obvious outgassing.
Precisely. It got a small but definite velocity boost after swinging past the sun, a boost that couldn't be explained by gravity alone. Trying to explain it with standard cometary outgassing just didn't work, because telescopes saw no dust or gas around it that could provide that thrust. It was like a silent engine kicked in.
And it looked weird too, didn't it? Not like a typical rock.
Very weird. Unlike 3I Atlas, which seems to be developing a coma and tail, Oumuamua was dark, reddish, and had a very extreme shape. Descriptions ranged from a cigar shape to a flat, pancake-like disc, extremely elongated, maybe 240 meters long, but only 40 meters wide or thick. That's a 6-to-1 aspect ratio, maybe even more extreme.
Which is just not something we see in natural asteroids or comets usually. They tend to be lumpier, more potato-shaped.
Exactly. Gravity tends to pull large objects towards spheres, and even small ones rarely have such extreme length-to-width ratios. Plus, it was tumbling end over end roughly every 8 hours.
So dark, weird shape, tumbling and accelerating mysteriously. It ticked a lot of unusual boxes.
It really did. And this collection of anomalies led astrophysicist Avi Loeb from Harvard and a few others to propose something quite radical. They suggested that maybe, just maybe, Oumuamua wasn't natural, that its strange shape and unexplained acceleration could mean it was an artifact, an alien probe perhaps, or even a light sail.
A light sail, like a craft pushed by sunlight.
Or starlight, yes. The idea was that maybe its flat shape was designed to catch radiation pressure, explaining the boost without needing rockets or outgassing. This hypothesis gained traction mainly because the conventional explanations just seemed insufficient to cover all the observed facts, especially the acceleration without a coma.
So, with Oumuamua setting that precedent of deep strangeness, people started looking at 3I Atlas differently.
You could say that. Inspired by Oumuamua's lingering mysteries, some theorists have started weaving a narrative connecting the two. In this view, Oumuamua, being smaller, faster in some respects, and exhibiting that weird acceleration, is cast as the scout.
A reconnaissance mission sent ahead.
That's the idea. A probe sent to quickly survey our system, gather data, and maybe report back or move on. And following that logic, 3I Atlas gets labeled the vessel.
The vessel. That implies something substantial. A mothership. An ark.
It implies something larger, perhaps carrying more payload or having a different purpose. The theory suggests it might be a deliberate follow-up to the Scout. And intriguingly, part of this narrative suggests it might be cloaking itself. using its developing coma and tail, which look like natural cometary features, to hide its true, possibly artificial nature.
Like hiding in plain sight. But you mentioned earlier that 3i is actually faster than ʻOumuamua relative to the sun. How does that fit the follow-up idea?
That's where interpretations diverge. While the measured solar system velocity is higher, some proponents of the vessel theory focus on different parameters or suggest a more complex trajectory. They might argue its approach is more deliberate, perhaps slower in some calculated sense relative to a specific target or objective within the system, rather than just a random high-speed flyby. It really shows how you can spin the same data points to fit a pre-existing narrative, especially when dealing with unknowns.
So the core idea is that these aren't just two random interstellar rocks, but a sequence, a planned arrival.
That's the essence of these fringe theories, that we're witnessing a deliberate sequence, perhaps a message, or part of a larger mission, orchestrated by an extraterrestrial intelligence rather than just the chance passage of natural objects.
Which obviously opens up huge questions. Are these probes? Arcs carrying something? Messengers?
All those possibilities are floated within these speculative frameworks. The idea that these could be highly sophisticated artifacts, not natural phenomena at all. And this is where Avi Loeb and others have pushed further, publishing research exploring 3I Atlas specifically as a potential extraterrestrial spacecraft, and even raising the possibility based on theoretical grounds like the dark forest hypothesis that it might be possibly hostile.
The dark forest. That's the idea that civilizations stay hidden because contact is inherently dangerous.
Yeah. Essentially, yes. It's a grim potential solution to the Fermi paradox, why we don't see evidence of aliens. The idea is that maybe the smart strategy in the cosmos is silence, because any civilization you reveal yourself to might see you as a threat and eliminate you first. So in this context, an arriving vessel might not be friendly. It's a stark contrast to more optimistic first contact scenarios.
Loeb also mentioned suspicious timing.
Yeah.
About perihelion.
Yes, he pointed out that 3I Atlas reaches its closest point to the sun, perihelion, around October 29th. During that time, from Earth's perspective, it will be largely behind the sun, making detailed observation very difficult.
Hidden by the sun's glare.
Right. He suggested this could be intentional, a way to avoid our closest scrutiny during a potentially critical phase. He also suggested its overall trajectory seems aimed towards the inner solar system in a way that feels more like navigation than a random path.
Implying intent.
That's the implication he raises. And these discussions sometimes branch into concepts like von Neumann probes.
Self-replicating probes.
Exactly. The theoretical idea that an advanced civilization could send out probes that use local resources to build copies of themselves, allowing for exponential exploration of the galaxy relatively cheaply. Could ʻOumuamua or 3A Atlas fit that model? Well, one counter-argument that arises is the size of 3A Atlas.
It seems awfully big for just a probe, 11 kilometers wide.
That's the question some ask. If you're advanced enough for self-replicating tech, couldn't you make your probes much smaller, stealthier, more efficient? Why send something mountain-sized if observation is the goal?
Unless observation isn't the only goal.
Or unless our assumptions about advanced technology are wrong, but it adds another layer of complexity to the speculation.
And these theories also touch on the immense travel times involved, thousands of years.
Some calculations based on its trajectory and potential origins suggest it might have started its journey or been launched perhaps over 8,000 years ago. It just underscores the mind-boggling scales of interstellar travel, requiring either incredibly long lifespans, generational ships, or perhaps dormant technology waiting for activation.
As with every episode, we entertain the possibilities. But if you're familiar with our episodes, this is the part where we return to the data. This is where the science has its say.
And despite all the fascinating speculation and the genuinely unusual aspects we've noted, the strong consensus within the mainstream astronomical community is, well, much more grounded. The overwhelming view is that 3I Atlas, based on current observations, behaves like a classic, albeit interstellar, comet.
So the hyperbolic orbit just means it came from far away, but doesn't imply artificiality.
Correct. That orbit is entirely consistent with natural processes. Think about the early days of a star system. Planet formation is messy. Giant planets migrate, smaller bodies get scattered everywhere through gravitational interactions, or maybe a close pass by another star could eject objects from a system.
Cosmic billiard balls, essentially.
Pretty much. These processes are expected to fling vast numbers of comets and asteroids out into interstellar space over billions of years. It's perfectly plausible, even expected, that some would drift into our system eventually.
And the coma and tail formation. That looks normal now.
Yes, its overall activity pattern, the development of the coma, the formation of a tail as it nears the sun. These are all textbook signs of volatile materials, like water ice, sublimating off its surface due to solar heating. And crucially, recent spectroscopic observations have reported finding evidence of water ice signatures in 3I-8Ls.
Water ice, the most common stuff in comets in our own system.
Exactly. It strongly supports the cometary interpretation. People like Dr. Daryl Seligman, a prominent comet researcher, have stated quite clearly that the telescopic data shows classical cometary signatures. He argued the initial lack of detectable chemicals wasn't mysterious. It was simply because the object was too far from the sun initially for strong outgassing. As it got closer, the expected activity kicked in.
So the early anomalies might just have been due to distance or its specific mix of ices.
That's the most likely scientific explanation. Other scientists have also pushed back against the more extreme speculations, arguing they distract from the actual scientific work needed to understand this natural object. They firmly state it's a comet.
And finding it isn't actually that surprising anymore, with Oumuamua and Borisov preceding it.
Not really surprising to astronomers who model these things, no. The discovery of 3I Atlas actually reinforces the long-standing theoretical prediction that our solar system should be constantly visited by interstellar objects. Scientists have estimated for decades that there could be billions, maybe trillions of these objects drifting through the galaxy, and many passing through our system undetected at any given time.
We just didn't have the tools to see them before.
Precisely. Our inability to detect them wasn't because they were rare, it was because our technology wasn't sensitive enough or wasn't looking in the right way. Especially smaller objects or darker ones, they're incredibly hard to spot until they get relatively close or become active like 3I Atlas.
But that's changing now, with new observatories.
Dramatically. The big game changer is the Vera C. Rubin Observatory in Chile. It's expected to start its main survey operations relatively soon, around mid-2025. Its sheer power, the size of its mirror, the width of its field of view, and how rapidly it can scan the entire visible sky is going to revolutionize this field.
How many are they expecting to find?
Predictions suggest the Rubin Observatory could find something on the order of one interstellar object per year, maybe more. Especially if many of them turn out to be active comets like 3I Atlas, which makes them brighter and easier to spot.
So we might go from finding one every couple of years to finding them annually or even more often.
That's the hope and the expectation. And managing the sheer flood of data from Rubin requires new techniques too. They're developing sophisticated machine learning algorithms, training them on simulated data to automatically sift through the nightly observations and flag potential interstellar candidates almost instantly.
Using AI to find the needles in the cosmic haystack.
Essentially, yes. It's necessary given the volume of data.
So what's next for observing 3I Atlas specifically?
Continuous monitoring, NASA ground-based telescopes worldwide. Everyone with the capability will be tracking its brightness, its activity, its coma composition, its tail dynamics, trying to get that rotation period, every possible detail. There's even talk that missions already in space, like OSIRIS-APEX, which is now heading towards asteroid Apophis, might be able to do some long-range observation as 3I Atlas makes its closest approach to Earth's orbit.
Drawing on experience from missions like Rosetta.
Absolutely. Rosetta's long-term orbital study of Comet 67P and the Philae landing gave us unprecedented insights. Same with NEAR's mission to Eros. We learned so much about the rugged, complex surfaces of these small bodies, the sudden jets, the strange terrains. All that experience informs how we approach observing 3I Atlas.
Even though a flyby is much harder than an orbital mission, right? Because of the speed.
Much harder. The relative velocities for interstellar objects are huge, tens of kilometers per second. That makes a close rendezvous incredibly challenging. We saw the risks with Giotto at Comet Halley back in '86. Even a tiny centimeter-sized dust particle hitting the spacecraft at that speed caused significant damage and destabilization.
A reminder that space isn't empty, especially near an active comet.
Exactly. It highlights why, for any future dedicated missions to intercept an interstellar object, we'd need really advanced tech. Things like highly autonomous navigation to dodge debris, maybe smaller, disposable probes for the riskiest parts of the flyby.
But the scientific payoff for studying these objects is huge.
Immense. Every interstellar object we study gives us a direct sample, a piece of evidence from another planetary system. It helps us understand the range of conditions out there, how other systems form and evolve, and ultimately how common or rare systems like our own might be. It contextualizes our place in the cosmos.
Whether scout or vessel, natural relic, or distant messenger, interstellar objects like 3I ATLAS remind us that the universe does not begin or end with the sun. Things move through it. Some leave no trace, others leave questions. For now, 3I ATLAS remains what it appears to be, a comet, a very large, very fast, very interesting interstellar comet. But we'll be watching, because someday, one of these objects won't just pass through, it will arrive.
That's it for this journey beyond the known. If the unknown speaks to you, liking, subscribing, and following truly helps us grow in these early days of the channel. And if you'd like to help even more, consider becoming a member at any level. You'll get early access to deep dives like this one, the audiobook Underground, hand-curated wonders, and you'll even get a say in shaping what we explore next.